first of all, welcome to the social network analysis tutorial for PyCon. This is the second year we're doing this. If you Google our names, you're going to see that we've done this before. And there is actually quite a bit of stuff on YouTube as well, going into some of the gory details of how to do this. So there is plenty of reachback. There's probably about 6 or 7 hours of video on YouTube of me doing webcasts on this topic. So about a year ago, Alex and I published this book, Social Network Analysis for Startups. It's, I have to say, on the bestseller list for data analysis books on Amazon. It's number 70 on the top 100 data analysis books, which is pretty cool. For PyCon and for others, if you want to buy this book, you can use this discount code AUTD5 on O'Reilly.com, and you're going to get a 50% discount. Also, the books will be available at I think a 40% discount tomorrow, and I'm going to do a book signing. So yeah, so you can come and talk to us in the O'Reilly booth downstairs, where we'll be talking to anybody about this tomorrow. I think about 6:30 during the reception. So anyway, when we talk about social networks, we will talk a little bit about the social networks, Twitter, Facebook, et cetera, et cetera, et cetera. But social network analysis is way bigger than this. So the online networks, they give us some of the best, quickest to access data sources. But at the same time, they don't give us data sources that tell us the most interesting stories. So what we'll show is there is a couple places. There is actually hundreds of places you can get data nowadays, and there are a few places that are not thought of as a social network that can provide incredibly rich background, incredibly rich stories about the world. So I want to do that. But we'll do Twitter too, just because a new pope has been elected, and Twitter is a buzz, and we'll get some of that data to play with. So what is social network analysis? In a nutshell, what we're doing is quantitative analysis of relationships. So if we went and said, hey guys, let's do regular statistics on people. We get a set of observations. We observe a number of variables about the people. And one of the biggest parts of statistics, traditional statistics, econometrics, regression analysis, etc., is what's called as independence assumption. And this is part of the, it's also the alternative name is the Poisson assumption. So, and the idea is that if you were to toss a coin twice, the result of those coin tosses are completely independent of each other. So in social network analysis, the first thing we do is we dispense with the independence assumption. And what we say is our observations being usually people, but sometimes also organizations, computers, networks, conferences, any kind of other entity. But our entities are precisely defined by the fact that they are dependent on each other. There is no, and we're going to analyze those dependencies. That's what social network analysis is really about. The other way I would describe this is that a node in a social network. So a node is an entity, it's a person, organization, blah, blah, etc. So a node in an organization is a noun, and a relationship is a verb. And that is really the easiest way to tell a story using social networks, because you can now compose little sentences. person X likes person Y. One of the things we're going to show is Congressman X co-sponsored 5 bills with Congressman Y. So really what we're talking about is a verb or a verb phrase. Some of you, especially if you've worked for the government, and by the way, I live in Washington, D.C., and Jackie lives in Washington, D.C., and we deal with government people all the time. And if you work for the government, you're going to see a lot of people using something called link analysis. There's a company started, actually the company is located out here in the valley, called Palantir, that is huge in link analysis. We're talking about hundreds of millions of dollars in revenue, started by Peter Thiel. What they do is it looks like network analysis. It visualizes like network analysis, but it's not. And the reason it's not is it's qualitative in nature. It's all about describing things, not calculating things, not measuring things. And the way I see this is, link analysis is a distant cousin of network analysis. Unfortunately, then there is a problem when they try to apply quantitative metric to qualitative data, and the results are garbage. But I don't want to go on a 30-minute rant talking about what's wrong with link analysis. And that's kind of what it looks like. I just want to show you some examples. So this is from Flickr, and this is who's been tagged in whose pictures. And this is just a tiny snippet. And of course, Flickr networks are huge. This one is actually very interesting. And you cannot read this because so this thing is actually poster sized. It's like 40 by 80 inches. The smallest, so this is all about how scientific fields are related to each other. And they're related through, so like you can see Earth, body, motion, etc. So they're related through common terms, through common ideas. And if you actually took a magnifying glass to a full resolution poster, you would be able to see names of most published scientists on this. So this is a network. There is a couple other things here. Robert Dunbar. So I'm going to name drop a little bit people that you can look up. Robert Dunbar is an anthropologist from the UK. He's been studying regular patterns in how different apes and also different human societies shape their networks. And one of the interesting things that happened there is that, so he discovered that the average size of a social network, so average size of your Rolodex, and he actually measured this by people sending Christmas cards. The average size of a human social network for any individual is about 150. Now Facebook and Twitter changed things a little bit, but the in-person equation is about the same. For others, for apes, it's about 20 or 30. And sort of the more primitive someone's brain is for a species, the smaller is, or less complex their social grouping is. So what happens here is that, sort of a natural size for African villages, if there is no market or crossroads or sort of serious external reason for their existence, the average size for an African village is about 160 people. In a Roman manipula, there was 150 people. Also in the company in the American Army, it's 100 to 150. Facebook friends average is 150. So on the other end, so immediate family and best friends. So we have, this is really tight connections. If there is about 6.5 people on average for an American family. a small startup under two pizza rule by Steve Jobs is going to be about 5 or 6 people. Terrorist cells are about 6 people. There is some regularity here. What happens here is that at the top of this pyramid those are people that you interact with daily or more than once a day. Those are really your close-in cohort. And as the pyramid expands in numbers, the amount of emotional energy, the amount of investment you put into each one of those cohorts gets lower and lower. So 150 is about as many people as you can keep track of on a first name basis. From that point on, if it's a company, you have to start developing a lot of rules and procedures. If it's your Twitter following, well, you're not investing when you have 8,000 Twitter followers. Your follower number 7,999 is not going to get a lot of your emotional energy. Sort of a position of a network link in this hierarchy in terms of time and energy invested can become very valuable. And we'll talk about how to approximate this from the data that we can get. The other thing I can tell you about networks is they change. So an organizational chart is a network in a way. It's a kind of stupid network, but it's an it has nodes and edges, and the verb on the edge is reports to or manages. So here's an example. One of my teachers, David Crackhart, used to run this example all the time, so I take after him. So we have a small consulting firm, actually auditing and consulting. They have a group of accountants, they have an IT group, and they have a pool of secretaries that manage the paperwork. And there is a lot of paperwork in their field. They hire a consultant at some point who reorganizes the company like this. And so on one hand, if you went from sort of strict departments to group of people working with each one of the clients, they get a lot of efficiency from that. On the other hand, the number of mistakes goes through the roof. And they nearly land on the front page of Wall Street Journal with some really bad accounting shenanigans. So David Crackhart was brought in as a consultant to help save this company's butt. Because they were failing. So what he did was he tried to gauge the social network in the company. He took the original org chart as a social network. He took just by talking to people a measurement of who trusts whom, who goes to whom for advice, and also who goes for beers together after work. So we have two different kinds of. We have the formal network, we have the informal network, and we have the really informal network. So there's your formal network. That's really the same picture, just drawn differently. So the green nodes are secretaries. Just people who just did the paperwork. And this is what the informal network looks like. So we have a company that is not run by the CEO. We have a company that is run by one of the secretaries. And the CEO seems to, he talks to her and he asks her for advice. But the problem is, if you look at this chart, this powerful secretary is actually removed, and she's not even in the office a lot because she's working on the client side. So that's the root of the problem. So they ended up promoting her to, like, from senior secretary to like chief of organizational learning or something like this. She jumped all the way into the C-suite, and all she did was teach others how she does what she does. Why do I actually pull this out here? This is, a really organizational consulting talk. The reason I'm pulling this out is to show that there are multiple layers to any network. You know, we can observe different kinds of things going on. You know, if we look at formal, we will observe something completely different if we look at informal. It's enough for us to just ask a different question, and we're going to get a completely different picture. So a lot of the things we do here are about zeroing in on what the real structure is and how the structure works. I want to give you an example of a network that is not people. So this one, it's really hard to read at this resolution. This is a network of hashtags. So looking at some Twitter data, and I'll show you later how to pull the hashtag networks. So this is a network of hashtags. This one is actually old. It's related to the revolution in Egypt a couple years ago. And when we cluster this, what we're going to see is this part here. This is highly relevant. This is highly relevant tags talking about Tahrir Square, talking about revolution, talking about Mubarak, all of this. This part is unrelated news. One of the big things, the reason this got pulled in is the royal wedding in the UK was at the same time. So happens to co-occur at the same day, gets pulled in. The cluster up on top is spam. If you look at hashtag networks, this is actually one of the most effective ways to isolate spam on Twitter. It's incredibly fast. It's incredibly easy to see. It just pops out. Here's another Twitter network.
Maksim,
Yes.
can you just explain what the edge is?
Yes. Yes. So the edge is co-occurrence of hashtags. So if I use two hashtags in the same tweet, we get an edge. If two people use the same two hashtags, the edge gets a little thicker. So here we actually said 100 people need to use the same two hashtags together, 100 or more. So this, in a way, is I call this poor man's latent semantic analysis. It's a lot easier to do than proper latent semantic analysis. And it's actually a lot faster in terms of machine time. And it gets you very close to the same results. And we can do that on pure language as well. So co-occurrence networks in text are also quite powerful. So yeah, so this is the retweet network also for Egypt. So and what you see here are those clusters. Each one of those clusters, this is actually trimmed up. I couldn't fit everything on screen. Each one of those clusters is over 1,000 people. And we just have the big nodes are people who have gotten a lot of people to respond to them. So what we'll show you is basically how to find this. This is where you get the influencers. This is where you get an idea of who is getting things to pop and who is getting, who is getting big responses. We're going to do a couple other things. I want to show you sort of this big slide. There's lots of other pictures. There is a lot of things you can do with this. So I'll give you a rough bit of an agenda. So right now, Alex and Jackie will take over, and we'll talk through the setup, and possibly take a little setup break to make sure everybody that wants to be up and running is up and running. And then Alex will talk about getting data from Congress. So we're going to start. We're going to start today not with Twitter, not with Facebook. We're going to start with mining the Congress API and figuring out what the hell is going on in Washington. We'll see if we can find some interesting insights in that. Then I'm going to switch and talk about harvesting data from Twitter and how to get at some of the insights from Twitter networks. And then we have some quantitative metrics. So we're going to take a break and after that and do more quantitative. Hopefully we'll have enough time to get to clustering today. So guys, you want to take over? Let me mic you up.
I can just use that.
Oh, you can, yeah.
Yeah, I'll stay here.
You're good?
I'm going to tell you to give this to somebody.
Okay, give it to.
Yeah, start it on that side of the room because I think we have two
Okay.
on this side.
So,
Hi.
okay?
Yeah,
I guess,
I'll explain what's on that.
Okay.
So I'm Jackie
dragons.
Kazil. I'm going to be talking a little bit about setup. So on those jump drives that we have floating around, there are a couple of different files. There's a folder of packages if you have any problems downloading them. There's the Twitter JSON file, and there's also a copy of the repo. So essentially, everything on those jump drives should allow you to be off the network, theoretically. So we had the link up to the repo earlier. There's a requirements.txt on that, in that repository. And you should be able to install everything to get it up and running. The major things that you need are matplotlib, NumPy, and NetworkX. And just as a warning, matplotlib requires NumPy, so you want to install NumPy first. So you don't go to install matplotlib and then get an error. The Git repository. I actually posted a link on my Twitter account. If you, it's twitter.com/Jackie Kazil, JACKIEKAZIL. It's like the last second tweet, one of the last two tweets or something. Anyone else? Yes. Yeah, thumb drives. Where are the thumb drives? Raise your hands. Okay, how many people have done the thumb drives? Okay, a couple. So they're bouncing around. We have 3 of them in the room. If anyone has a spare thumb drive, I'll make another copy and start passing it around if you want to lend it to us. So basically, you want to have an environment and install the requirements. We also, thank you. And I'll get that back to you in a second. And then we also have some IPython notebooks. There's instructions for the IPython notebooks and the requirements for those in the README in the repo. Those are not required. Those are just sort of nicer ways of interacting with the content. But you can certainly follow along with a Python interpreter. Yes?
Sorry, what was the Twitter again? Jackie, J-A-C-K-I-E?
Kazil, K-A-Z-I-L.
K-A-Z-I-L.
Yeah. So how many people are still installing? So let's ask that. Okay, so we still have a couple of people. Do we want to do a help around the room and take a break?
Yes.
Okay.
So, let's do a quick install break.
The files you have on your thumb drives, you can install them with easy install. Once you have set up your virtual environment, you just say easy install file name, and it will install it into the virtual environment you just created.
File name being the path
To the
specific package.
Right. Yeah.
7 of them or whatever.
Mm-hmm.
Can you just say start.egg or something for all of the eggs?
You could do a setup and create an egg.
Okay. Oh, okay. That's
Probably could. Yeah.
They just have eggs.
okay. That's fine. So shall we?
Okay. Yeah.
Okay.
Go ahead.
So guys, while we are while everybody's installing, we'll talk through some of the basic ideas in NetworkX, and then start gathering data.
Right.
Okay.
Okay.
And before he starts, I'm just going to interrupt him.
Yes.
And say I still have a couple of jump drives that are loading. It's going to be a few minutes. I will kind of wave over here with your jump drive in the air because I don't remember who gave me what. So hopefully we can get those jump drives back to you pretty soon. Continue.
Mm-hmm. Okay. So hi everybody, I'm Alex. I'm glad to be here, second time as a local now. So without further ado, I'll jump to the go through this stuff quickly. So we use NetworkX for our research, and so NetworkX it's a library for working with graphs, and it's based there's a graph container. So when you, and don't worry, it's in our last year's GitHub, but we'll move it over this one, so you'll be able to get it after we're done with the talk. So to use it, you import. Creating a graph is very simple. You just say, .graph and it creates your graph, and then you can add some nodes to it. And nodes can be anything as long as they're hashable. That means it cannot be a dict, it cannot be a mutable type. But strings, numbers, tuples, simple objects are fine. Right. So after you've added some nodes, you can recall them, and it will tell you, oh, we've added these nodes. One interesting thing that's happening here is you can say add nodes from and give it a list. If in Python, if you treat a string as a list, it's just a list of characters, so you get A, D, S, and F nodes as well as 1 and 2 in there. And has anybody used NetworkX before, by the way? Okay. Just wanted to know. Okay, so there are some other useful methods. You can also get an iterator over your nodes because likely your networks are going to be huge, so you don't want to get the whole list and look at it. You want to be able to iterate over it like this, and so you see this gives you the exact same thing. How does this work? Yeah, you don't have to write this down. Should we, Jackie? Should we point them at that notebook?
I'm actually just copied it over.
Okay.
And I'm about to add it to the
Okay, so it's about to appear in our repo, this notebook you're looking at. So you don't.
The problem is that we cannot see it because it's way down the screen.
Oh yeah.
What's on the screen?
Oh,
So, yeah, so
they
scroll
can
up.
see the bottom of this. Oh,
Yeah,
I see.
so scroll, yeah.
Just scroll. Why don't I just do this? How about now? Whoops. Is it better? Yeah? Okay. Oops. Okay. So going up further. And once you have a network, you can do a draw. And this, if you haven't used IPython Notebook before, this is IPython Notebook, and it does a few nice things for you. It preserves the output and it lets you sort of publish your work, and it still remains interactive. But usually you wouldn't be using it for your normal research, just because of the way it works with pictures and everything. But it will draw things for you very nicely. If you were doing this in regular IPython shell, you would have to execute another command to actually make the graph appear, but then it's manipulatable, and Max will show you how it's done. So once adding nodes is fine, how do we add edges? It's very simple. You just say add edge and give it a name of a node, or give it the node itself that you're adding the edge to. And the edge doesn't actually have to exist in your graph. If it doesn't exist, NetworkX will add it to your graph. So you can just say, add edge from 1 to foo, and it will be there. And this is our new graph. We've just added 2 edges from 1 to 2 and from 1 to foo. And the rest are unconnected. They're still there. And you can, of course, peek inside and see what the object looks like, and contains a lot of information about the actual graph, like adjacency lists, the edges, and whatnot. The graph works like a dict. So you can say, node returns you a node dictionary, so you can say node and give it the node object, and it will tell you who it's connected to, I think, right? Or yeah, it gives you a list.
No, so it's a little bit confusing in the library. So we can do 2 different things here. So let me. So if we did.
I don't know if it's live, but try.
Okay. Yeah. So we can do this, and that will give you a dict with the nodes. But we can also do this.
Yeah.
And that will give you the edges. So the unfortunate bit, and I did not write the library, so.
Oh, you broke it.
No, I didn't. Did I?
Yeah. It's not live, so.
Okay, I need to regenerate the graph.
No, don't regenerate it. It might break again.
Okay.
Oh, it is live. It's working.
It is live. Okay, good. So if I did this instead, it will show me dict with the edges.
Yeah.
So it's a little bit confusing for no apparent reason, but we have to deal with what we have to deal with.
Okay.
So this library was developed at Los Alamos National Lab, and there's ones who maintain it. I've actually put this in as a bug report that apparently is a very low priority on people's list.
Yeah.
Go ahead.
Okay. So we can also manipulate attributes of nodes and edges. For example, say we want to add a weight to our edge, and NetworkX doesn't treat attributes specially, does it? Right? You can an attribute
it's
can be
just a
anything,
dict.
but you can later, when you're doing your traversals, you can tell it, I want to use this attribute as my weight, right? And to get an edge, you can simply say it's a double dict reference. So you say, if you say node at 1 at foobar, it gives you an edge from 1 to foobar if it exists, or if it doesn't exist, it will create one. And no, I'm sorry, this is not an attribute.
It's
This is the actual value of the edge, because
Right.
edges are objects too, right? So you can assign. Here is NetworkX comes with some example generators, and they have there's a package called small, and there's a package called, I think, medium and large, that generates some of the more common graphs. So this is
Those came back.
this is Max. Do you want to? Okay.
Yeah.
This-
So hold on. We have 2 flash drives available with stuff already on it. Whoever needs to install. Okay.
And then I have 2 more, which people provided me, and those are the last 2 I have.
People been able to easy install.
Have you installed NumPy?
Yeah.
Oh.
First.
Yeah. I think you just easy installed in the name of the file, and it should work. But we were fortunate to have the time to wait on the connection for for the regular pip to work. So, and yeah, so I think Jackie will find out. But getting back to it, a typical small example is a Kragart kite graph, and Max, you want to
Yeah.
say what it is? Or it's
Well, actually, just draw it.
I'll just show.
Oh,
Yeah.
Yes.
It just gives you by default 10 nodes, and they're connected in this special way.
That
And it
looks like a kite.
this. It looks like a kite. That's why they call it a kite graph.
Yeah. So this is basically an illustration that is used. We'll use it a couple times when we talk about centralities. It's a good illustration because it shows strengths and weaknesses of different quantitative metrics on something that's very tiny.
Oops. Next to Dix. Okay. I don't think we need to go into this. All right. So Max will show you more neat manipulations of graphs. Should we cover
Let's do Congress.
Congress? All right, Congress. So when we were looking at data for this presentation, we were looking at Open Congress to get Congress data, and turned out that Open Congress actually uses GovTrack, which is a what is it? Is it
So
Is-
GovTrack is a nonprofit in Washington D.C. that mines and aggregates data from Congress, Federal Election Commission, and a number of other data sources, and makes it available to people so they can track, what's happening in Congress. So this data is actually available basically for straight up download. What's the format?
So there's multiple ways you can do this. It's all, you could rsync it, and they describe it all in their documents. You can actually browse the directory and see what it looks like. Whoop, here's here's some bills, and you can,
Right.
and they're kind enough to put it in JSON, not just XML. But they also have an API, which is what we used. The API has several entry points, so you can look at bills, people, voting records, co-sponsorships, and we wanted to pull in we're building a graph of co-sponsorship to see who co-sponsored what. And just to give you a little, okay, I won't. This is on GitHub, and you can look at it.
Yeah. So we've built up an API client for this that we're sharing with you. It's not actually, it's released on GitHub, but it's not sort of it's not its own package yet.
Yeah, it's something very quick and rather
a few
simple.
hundred lines of code.
Yeah,
but it will call on the API and it will fetch bill co-sponsorship data from the API endpoints.
Yeah.
So here's
an example of the call. So you refer to this URL and you get a nice JSON about a bill, and you can get many bills at once. And so all this API does it hits that URL, and it also supports paging because they will give you a fixed number of results, but they tell you how many results are left, and it will look at that number and page everything, stitch it for you.
Right. So the way Congress works is, this is sort of, the Schoolhouse Rock, I'm just a bill. I don't know if anybody remembers that cartoon. The way the House of Representatives works is that the representative introduces a bill. Usually it's the highest profile person that either the bill is either related to their jurisdiction or their committee assignments, and then a number of people sign on as co-sponsors. For some bills, maybe the entire House of Representatives might sign up as a co-sponsor. Usually it's, this would be for something innocuous like renaming the library or something like this. Then those are actually bills that people do vote on. For other bills, it's a little more controversial. Any bill that raises taxes or cuts benefits or does anything politically uncomfortable is going to have fewer co-sponsors, either on strict partisan lines, or occasionally there are bills with no co-sponsors. And as Jacqueline was actually saying that she's seen some bills that have no sponsor. So they're introduced by a member of the House of Representatives almost anonymously. What we want to study with this is whether or not the co-sponsorship network can show, whether we have any collaboration going on in Congress, whether anybody crosses party lines at all. So this is kind of data we can answer questions on, how did the climate change in Congress, let's say in the past 10 years? We have some idea of what happened, of course, from reading the news and from following the politics, but this can actually give us data. So we'll show you a small sample of that. We'll just look at about last year's worth of bills. That was 16,000 bills or so?
No, there was more like 40,000 bills.
40,000 bills.
Yeah.
And so and a lot of those are, very simple things like it takes an act of Congress to rename a post office, or to open a new post office, or to close a post office. And those are decided on about 15 minutes, but it's still a bill. A bill is still a bill. So Alex, so
just some quick examples of our API is very basic and it's quite simple to use. So you can just import it and like you can just get any 10 bills and it will give you a result like this. Tells you which URL it called and the contents of the thing. So you can give it limit 50,000 and wait for a while and it'll give you 50,000 bills. But you can also do things like Congress. Oops. Equals 113, and it's running, it's getting, it's depending on the network, if we're lucky, there it goes. So there's 10 bills from 10th Congress. And there are different ways to filter the results. They're all described on GovTrack API, which different keys you can use. You can do sorts, you can use dates, it's quite powerful. So once you get this, what do you do? What do you do with it? I wrote, a simple little storage thing to where you take the object that the call returns, which is just a list of JSON objects, which are the bills, and also people, and also co-sponsorships, and write them to a file. And this is the files. These are the files that are checked in. So we have the bills from Congress 113, which is the current one. We have a file of all the people, and I think it probably helps to show what so this is what a person dict looks like. Has a bunch of information about a person, tells you which Congress they've served in. It has a lot of nicely structured data. And finally, co-sponsorships. Co-sponsorships look even more simple. Yeah. So it just gives you a bill and tells you who also sponsored it. So like bill number 4 was sponsored by all these different people. And this is the piece of code that constructs the graph. So here we create the graph, and here we read in the objects that we've just saved. We turn them into dictionaries, like so. Does that, oh, oops. And we use them as small in-memory databases because they get indexed by the ID of, bills are indexed by the ID of the bill, people are indexed by the ID of the person. And co-sponsorships is just a list that will iterate over. So for each bill that we see in co-sponsorship that looks like this, we're going to pull out the actual bill if we have it, because the collections don't completely overlap. We pull out the bill, we get the ID of the author, the person who introduced the bill, we get his name, and we get the name of the person who sponsored it, like this. Oh, and I forget that people can't see it in the back, so I'm going to, there. Yeah. And we add an edge or increment its weight, if it exists. And at the end, we get our nice, pretty little graph that, oh yeah, I also had which is, this is an example of calling the API directly, which shows you exactly what we just showed. And so the upshot of this is you just import this net module, you run this, and it gives you a graph of co-sponsorship, and it looks like that. And now Max will show you what it looks like in greater detail. Thank you very much.
Okay.
So what's the answer?
The answer to what?
Do they collaborate?
I'll show you. We'll get there. Okay, my microphone is now on.
Oops.
So
Before Max continues, I just want to say I think I might have got an answer on the matplotlib issue. It requires libpng and freetype to be installed either via homebrew or MacPorts. I posted more information to that to my Twitter account. So that probably is the issue of what the error is being caused by.
okay.
And as an industrial developer, I will just say this, that all you people that do this on your native Macs, and you bring the suffering upon yourselves at will. So I recommend using VirtualBox and running Linux in it, and it makes life just so much easier, so you don't have to deal with those issues.
Okay, so give me 1 second. So I also imported the same data, and I'm going to just get it up on screen. Can people read this? Or is this too? Okay, okay, perfect. Even people in the back? So let's try to do this way. Okay, so I created a co-sponsorship network from this data, and it had 536 members of Congress in it. So we have 538 normally, and I guess two people did not participate. So sort of a parliamentary anecdote. One of the most famous members of British Parliament, Isaac Newton, he really didn't want to be in Parliament, but he was the director of the Royal Mint that he was forced to. And he introduced a single bill that had no co-sponsors, and that bill was to close a window in the House of Representatives because it was House of Commons, because it was rather cold. That was the only thing he ever did as a member of Parliament. So we probably have a couple wall standers like this that the backbenchers, as they call them. They only show up at votes and not do much else. But almost everybody else participated in something. So let me draw this one more time. And since I'm not using IPython, I need to do this, plot show. And it shows up in a separate window. So the reason I do this is actually pretty simple. I get to manipulate this a little better. So here's, there is a zoom in tool. So I'm going to zoom in on this giant hairball. And so the first thing that happens is, one would think, okay, one hairball is Republicans and one hairball is Democrats. Well, actually, no. It's actually by Congress. So 112th Congress and 113th Congress have two different hairballs. So this is the first thing they're going to do. They're going to isolate the hairballs, and then we'll work through those. So the first thing that we're gonna do with this is called connected components. So connected components in the network is, well, the way you saw this, the two parts of the networks that were unconnected to each other, but they're connected internally. Those are called the components. So we're going to nx dot connected component subgraphs cn. And what it produced is actually it's actually a list of graphs. So in each one of them is a NetworkX object that can be manipulated just like a normal graph. So I'm going to call it C1 coms 0. Okay, so I'm going to just work with one of them. So start by drawing it. And so this is starting to look a little better. Not quite where we want it to be, but a little better. As you can actually see, there are some Republicans and there are some Democrats. You can see that there is a little bit of division between the Republicans and Democrats, but they're actually cooperating. Wow, that was kind of unexpected. Well, let's see what they're cooperating on, or how strong their cooperation is. Well, so what we did when we created the graph is we created a weighted graph. So all of the edges have an integer weight that simply counts the number of bills that a particular representative was on as a co-sponsor. So if we did the C1.edges and we say data equals true, so that will return to us a list of edges including the data. I'm just going to type out the first 10. And as you can see, we have weights. And the weights are all highly skewed. So you're going to see a lot of ones. In fact, let me see what the distribution of weights looks like. Equals data weight 4. Okay, so before I press enter, let me walk you through. So I'm using a list comprehension. And what happens here is this will give me an iterator over a triple from, to, and data. So this is the from, this is the to, and this is the data. And data is a dict. So all I'm doing is I'm grabbing the weights from that dict. And we got on a list of numbers. So now I say plot.hist. So that's a histogram. And plot.show. And it looks like this. So so most people have only there is 10,000 single co-sponsorships, and only like 1 or 2 people have co-sponsored large number of bills with each other. So this is actually very typical. This is called the power law distribution. If you look at strengths of Twitter connections, for example, number of retweets from one person to another, it's going to look exactly the same. If you look at the hashtag co-occurrence, it's going to look exactly the same. This is very, very common. There's a lot of single, almost chance co-occurrences happening, and there is very few stable relationships. So the first thing we're going to do is we're going to isolate those stable relationships. The way we're going to do this is, so in the repo, there is a file called utilities. So I'm going to say from utils import star. There's a number of functions in here. Let me show you. Okay. Yeah. So there's utils.py, and it has a couple useful things. The ones that I'm going to use is called trim edges. So it's right here. It's a simple function that all it's going to do is it's going to copy this network, and it's only going to keep edges that are greater than a certain threshold value. So here it defaults to 1. So C1 trimmed equals trim edges C1. Well, how many people are left in here? 401. So we've now isolated 100 more backbenchers that have only done one thing in their year in Congress, or that only signed on to one co-sponsorship. So well, let's draw that one. Well, there we go. This is the picture starts to look a little different. So it's still a hairball, but we now see, okay, we have Republicans on the bottom, Democrats on top. Some people cross the party lines. So I see Lamar Smith, for example, tends to co-sponsor more with Democrats. And there is a couple, Ed Perlmutter, that seems to be more on the Republican side. But let's trim it some more. So get rid of weight equals 2. and redraw. So now we see that there are some isolated pairs. Those might be interesting. Let me check. There's Jim Cooper, Tennessee, Georgia and Tennessee doing something together. Not surprising. Let's see, we have, yeah, and okay, so this is basically all West Virginia. This is Illinois and Indiana. So we're really talking about regional concerns of some sort. And now so this is actually starting to divide very cleanly. There it goes. There's the Democratic side, there's the Republican side. So aside from very regional concerns, there is actually very little cooperation between the two sides. So, if we continue drilling in, let me run one more iteration. It only takes a couple minutes. If we continue drilling in, you basically start seeing the strong patterns. So 3. Yeah, now even more singles showed up, and well, look at this. So I think we can see the Tea Party. So not only this shows you who cooperates with whom. If you keep progressively doing this, it starts showing you factions. The other place I've done this, this method, you progressively remove things until stuff shows up, until structure shows up. This is really qualitative. One of the places I've done this was looking at scientific publication data. So in the same way, who co-sponsored bill with whom, I looked at who co-authored a paper with whom. And I actually have, that code is also checked in, so you can do that yourself. If you look at that, you can actually see emergent scientific fields. So I published a number of papers in my scientific life with political scientists. I have a paper published with neuroscientists, and I have a paper published with a geologist for no reason whatsoever. There are people like me out there who are doing similar things, and you can actually see when a group of random dudes like me doing random things starts actually converging and doing. There is a new emergent subfield. It's called computational social science. That is merging of computer science, political science, anthropology, and a number of other things. So you see this, and suddenly there's a cluster that congeals. It's pretty awesome. Sorry, you had a question?
Sorry, I'm a little bit confused. So the weight of the edges is how many things they cooperate on?
Yes.
So
Yep. Yep.
you're reducing the threshold, you're pushing the threshold.
Right. I'm pushing the threshold up.
Is there an IPython notebook, or is there a file that loads the indices and loads all the data from the API?
Yes. Yes. So that is checked in. It's in SRC folder. Do you have? Yeah. It's in the SRC folder. Let me just bring this up on screen. 1 second. So there's our repository, and in source, look at GovTrack, and there is canned data here. And also, so API.py will pull data from the API, and net.py will generate the networks. So this is what Alex was showing a few minutes ago. API.py will call the Open Congress API, GovTrack API, and grab the data, and net.py will. It will basically take there are the JSON.gz files that will grab those files, read them, and create a network.
It's very hard-coded, but because of that, very simple to use. Just call
Yeah.
the co-sponsorship function that will give you the graph.
Yeah, so you should, there's the function, the co-sponsors. Yeah, since I have this on screen, I wanted to show you the utils file. It will be also checked in here, but it's, yeah, it provides a number of functions. There is the trim degrees, trim edges. Trim degrees does the same thing, except it removes nodes that only have one connection. So let me show you how this works. C1 TD trim degrees C1 T. So that's going to remove all nodes with degrees of this degree of 1. So I'll draw this and show. So very clean clusters start to emerge. We can zoom in on each one of them. And by the way, so each one of those clusters is a connected component. So if you did what I did before, say net.get connected components, it will isolate each one of them in its own separate network. So what I'm showing you here is basically how you can work with live data and you sort of surf the data structure. You see where it takes you. And a little later, we're going to get into more quantitative metrics. How are we doing on time, guys? 20 minutes till break. Okay. Okay. And okay. So there's let me show. Okay. Question. Do we want to talk about? And this is an up or down vote. Would you rather talk about getting more data from Twitter, or doing some quantitative metrics? So Twitter, can people take a vote?
What quantitative metrics?
Centralities. So we'll start with that. That's the simplest. Quantitative. Okay, we have a lot more hands. Okay, then that's what we're gonna do. Give me 1 second to pull up the slides, and they are will be up and running. And by the way, those slides are also in GitHub. Okay, cool. So, so centrality is sort of a yes, sir.
Sorry, sort of related before we get into this. Can you give us an idea on the limits of the size of a graph that you can use to do this and stuff?
So I have gone as far as hundreds of thousands of nodes. I think at this point your only limit, because this uses in-memory storage, your only limit is how much RAM you can dedicate to this. So on a 16 gigabyte machine, I have managed to do more or less everything on very large graphs. The thing you're going to die on is visualization. So the algorithm itself is order of n square. And drawing, after you compute the positions for nodes, what you're going to get still is a hairball. It all will look like a hairball. So for that, I would say if you well, first of all, the visualization of more than 1,000 nodes is not useful, because you're not going to be able to see much. But yeah?
I didn't want to interrupt.
No, go ahead.
I've seen visualizations with very many nodes that are useful, which you do by, if you can have the edges be transparent or
yes,
value nodes cluster in specific ways.
Right.
I don't know whether it's possible with NetworkX.
Yes, it takes a lot more work, but sort of the default, if you say nx.draw over 1,500 nodes, you're dead. For that, what I would use is large. There is a open source thing called Large Graph Layout, LGL, and it does some of the things out of the box. It has not been wrapped in Python though, so you have to generate files for it and then run the. It's written in C.
On that same note, I've been exporting with GraphML and then importing with the Java Gephi tool and visualizing 4,000 nodes interactively out of NetworkX and doing coloring nodes and then you get a good
Yeah, so Gephi is pretty nice. I've used Gephi a few times. Unfortunately, I've managed to, every time I gave Gephi a non-trivial data set, I got it to fall on its face. So I've been talking to their developers on and off, and we're trying to get it more stable and get better interfaces to it so you don't have to write GraphML files and stuff. Yeah, Gephi has some pretty nice visualizations that can give you better views. Yeah.
So is there a general approach when you move beyond that hundreds of thousands of nodes?
At this point, it really depends on your problem. So at this point, I think visualization is not really what you need. You're going to start having to do more quantitative work. So I'm
not worried about visualization.
Right.
I'm just worried about if you have a graph, say, a trillion edges. Is there a general extension of this, or is that just a separate problem?
Some of those, not everything will work on those edges. So some of the algorithms we use here are actually complexities order of n square and maybe even n cube. So that's going to be a non-starter. Other things yield very nicely to parallelization. So I've done some of this work in Pig, for example, running on a cluster. The clustering problems are actually what Google calls embarrassingly parallel. We use those with either Pig running on Hadoop or since this is PyCon, one of my favorite cloud providers is PyCloud because it lets me distribute portions of the code very transparently. So I've used PyCloud for some of the larger computations as well. Get, let's say, 1,000 nodes running on it, 1,000 machines. Yeah, we can. There are no turnkey solutions for very large graphs. We need to always think about what questions we're asking and what answers we want to get, and where do we want to get with it. Sorry, any other questions before we sort of start running again? Yeah? Okay, cool. So what is centrality? This is really the most basic thing we can do with networks. We have a bunch of nodes, they're connected. We want to figure out who's in charge. That's, almost everybody that does networks starts with this. Who is in charge? Who is the most central, who is the most powerful, who is the most connected, etc. In the most basic way, your number of Twitter followers is, a metric of that. That's not a very good metric, but it's there. And if you believe the number of Twitter followers, Justin Bieber is the most powerful man in the universe. I have trouble believing that. And actually, no, if this was true, it's not the world I want to live in. But degree centrality is basically the metrics that gives Justin Bieber the priority. So this is well, Justin Bieber network looks like this. He broadcasts to millions and millions of people. I think it was 21 million last time I checked, probably more now. He broadcasts in sort of the star network. Those kind of broadcasters have powers. They can reach a lot of people very quickly. Or in other cases, if it was an organizational network, somebody could be, a big boss. The inverse of the degree is actually kind of funny. Because it can stand for power, but if you just change what question you ask, it can stand for lack of power. So the example that I've heard was, if you want to see who is the most powerful person, look at the inverse of the number of keys he has in his pocket in a company. So a janitor has all of the keys but has no power, and the CEO has no keys because everybody opens doors for him. But of course, alternatively, the janitor who has access to all of the rooms in the building, he knows a lot of things the CEO doesn't. So it's all about how do we ask the question, how do we interpret the data. So a couple other things is degree. So here we have a person who is clearly in an interesting position. He's in the middle of things. He is, coordinating 3 groups somehow, and yet he is, in terms of degree, he is completely indistinguishable from everybody else. So that's not very useful. This basically shows that degree is limited. And again, degree is roughly just the number of connections you have. So in the Congress network, it's how many bills you co-sponsored with anybody, or how many collaborators you've had. And on Twitter, it's how many followers you have, etc. And the reason people use this is it's just the simplest to calculate. All you do is you look at, how many connections someone has. There is a curious bit about degree distribution. So here we have a degree distribution that is a Poisson, but guess what? This never actually happens in real life. What happens in real life is what I showed you before, this edge weights. It's straightforward like this. It's always, in any real network, it's always going to be power law. So it's always, there is a lot of people with very small degrees, and then there are celebrities with very large degrees. Happens all the time. So yeah, here's another example where degree doesn't work. So we have, again, the person in the middle, and he's by far, he's not the highest degree anywhere in the network. This, by the way, happens, well, this is very stylized. This is just for the purpose of showing you a picture. What happens if if you looked at the Congress data, there's a clump of people who are tightly connected with each other like this, guys. And then there is a person or 2 people that span connections between several groups. Those are called boundary spanners. And boundary spanners are very powerful because they can bridge divides in terms of information, in terms of, in Congress, in terms of partisan rhetoric. They understand what's going on both sides of the equation. So this guy is actually in a very powerful position, but degree is not showing it. So here's the next one. And by the way, all of those are available. This one is closeness centrality. All of those are available in NetworkX. And I'll show you how to run them very easily. So this is your distance. So closeness centrality for a person is his distance to everybody else in the network. And the rest, and then it's just normalized. So what happens is, if I'm in the middle of things, I have easy access to everybody else within a few hops. My ping time is low, so I end up being able to reach faraway nodes very quickly. So here's a couple examples, and again, in the star network, the Justin Bieber character also will have very high closeness, but in a network like this, we can now see, okay, the guy in the center, well, he has ability. He is actually very. He's actually the highest closeness score to everybody else. So that becomes very useful. The problem with closeness, and it's an unfortunate. There are 2 problems with closeness. One is it's a pain to calculate. It's very slow. So this is not something you want to do on millions of nodes. The other bit is if the network is disconnected. Well, your distance to people in the other cluster is essentially infinite. So there is a workaround for that that's been implemented in NetworkX, but it's not theoretically very sound. Yeah. Yes. Yeah, that's why it's a pain. You have to what you have to do is basically, so you run Dijkstra's algorithm on the graph, and you generate a distance table, and then you calculate closeness from that distance table. Here's a third metric that's even more a pain in the ass. It's called betweenness. And the idea here is this. So if I was to take a shortest path from point A to point B, how many paths from every pair of points A and B will pass through a particular place? And the easiest way to describe this is, so like in Washington, D.C., there is this intersection of highways called the Mixing Bowl. There is 5 interstates merging in one place. It's a traffic nightmare. What happens is if you wanted to get anywhere from anywhere else in the Washington, D.C. suburbs, on the Virginia side, you have to go through the Mixing Bowl. You have no way of getting from point A to point B unless you cross the Mixing Bowl, or you have to take side roads if it's clogged up. So as a result, the Mixing Bowl is probably one of the largest highway projects I've ever seen. They've rebuilt the whole thing completely. It still gets clogged up with traffic because of its betweenness. It's because you can't avoid it even if you wanted to. So that's the useful thing about betweenness. So in this case, betweenness doesn't work. So this is one place where we have this guy in the center who is, to us, he looks like, yeah, he is interested, he's central. Betweenness doesn't help him. Closeness does. But betweenness helps you see all of the other interesting ones. So I'm going to skip information centrality just because of time. And I want to show you this guy. So this is what you do. This is how you interpret this. So we usually calculate all 3 if we can. If we have time to run all of this, and then if we'll say, okay, so here's somebody who is high degree and low closeness. This is a person who is embedded in a cluster that is far away from the rest of the network. So, so he is in the middle of a group of outcasts. That group of outcasts itself might be interesting, or alternatively, this could be a group of spammers. So if you're looking at hashtag networks, for example, so that becomes a characteristic signature. Low betweenness, high degree. This is somebody who is redundant. He knows a lot of people, but information can bypass him. He's not the Mixing Bowl. Let's see, low degree, high closeness. This is a really important person. He's important. He may be a gray cardinal, but he is right next to the centers of power. Low betweenness, high closeness. Let's see. Yeah. So this is also a redundant one. High betweenness, low degree. This guy is in the middle. He has very few ties, but they're very important ties. He's a potential bottleneck. And this one is actually not very rare. It used to be rare, but not anymore. Perfect. So this one is cool because this guy is. There is a small group of people, and there is a large group of people that they have to be connected with. The only way they can connect through this guy is, the only way they connect to each other is through that one person. So he is low closeness, high betweenness, and we don't know about his degree. Could be pretty high, actually. what happens is this guy is a broker or a handler. And we see this in terrorist networks all the time. So there would be a cell of operatives that is planning something crazy. And then there is the rest of the organization that provides resources and does all of the other stuff. But the cell of operatives is connected to the rest of the organization through one person. And that one person actually becomes, well, a very big target for drone strikes. You know, the US military may or may not have been using this kind of metric. I do not have the clearance to know, but you know, there are rumors. Before we go on break, I wanted to show you very quickly how this is done. It's actually very easy. So d equals nx dot degree. So I'll use the C1t. And that gives us a dict with degrees. And C equals nx dot closeness centrality. Okay, and that's also a dict. And Venus centrality. Okay, cool. Yeah, so between the centrality, those numbers tend to be very low. A lot of them are close to 0. Yeah, so this is how you generate it. If you're using pandas, you throw all of those things into a data frame, so you get a nice table. You know, you try. One of the things that I've done in the past is try to create a compound metric. So if I know I'm looking for high degree people, high degree high betweenness or something like this, or I'm looking for boundary spanners, I would set up a set of weights and do compound calculation on them, and then sort it by that metric. Let's see, guys, what are we on time? Okay, so it's time for. So let's take a quick break. I think there is coffee somewhere, right? Is it?
In the morning there was.
In the mornings there was coffee, so I hope there is coffee in the afternoon as well. I can use one. So let's be back here. How long is the break supposed
20
to be?
minutes.
20 minutes break. So meanwhile, we are around to help you with installations and to answer questions and all of that. Cool? It will cut the periphery out in the middle. The middle is really what you care about. Right?
Well, in many cases, I care about this in a cluster. I've got a big graph, and I want to pick out a localized area where.
Yeah, so I'll show something for that. I've got the community detection. Community detection algorithms out there. So yeah, so we'll do a little bit of that.
Why is the code not part of NetworkX? A lot of the code that you're showing.
Why is what?
Why is the code that you're showing, a lot of it is in the repository, not back to NetworkX?
Partially because I've been writing utilities around that for a couple of years. I'm not a committer with NetworkX. I'm sort of an outboard contributor, and I want to become a committer, but so far I'm not.
Okay.
But I'm actually working on a fairly large module for NetworkX that will deal this multi-mode graph. It's a whole other specialty. So that will be committed as a part of the.
What is a multi-mode graph?
So multi-mode graph puts together nodes of different types. So you know, like Twitter, for example, is a 5-mode graph. There is 5 different types of nodes.
Well, what about different types of engines? Can NetworkX handle that recently?
Yeah, there is this thing called multigraph that allows you to do this, but it's not easy to jump along. So you're going to have to write code around it.
Okay.
Do you mind if we sort of walk out? We can walk and talk and see if I can locate some coffee.
20 minutes.
What?
You have 15 minutes.
15 minutes.
So these things that are sitting here, so what's the facility to install them so I don't have to go to the Smith one?
You can just drag and drop it.
Oh, really? They had
Oh, let's see. Yeah. Let's try
Oh, yes, yes. You need the stuff from the drive. Yes.
Those are the packages, right?
Yes.
I love it. So if I put it over to my so
Oh, this is yours.
yeah, this is basically that. The other one is
Right? SSH request. Have you ever done that before? It's the easiest way to get it. You can just speed up the code, just the requirements, I think.
Yeah.
So that's just a requirement, right?
Unless you're doing iPad on level 2 and you want that, then it's what's
Maybe Jim, you want to like do a quick run?
like the stuff is again?
Yeah, and how to install it.
Where are you? See this now.
Yeah. Okay, and I think Jackie's going to do a demo of how to install it. So it should, yeah. Yeah, all my Python stuff always.
I'm sorry. Can you move? Thank you. So people who are still having troubles with installs, I just want to go through this again and make some updates. So you'd want, let me make this bigger. That's too big. Okay. So there's some information if you have any problems installing matplotlib. There's a link now in the README. So basically what you want to do is create a virtual environment, or however you do it. If you don't use virtual environments, that's fine. You don't have to. And then install the requirements. If you got it from the jump drive, what you can do, which I just discovered, was pip install the tarball. So just do pip install and then the location of the tarball, wherever that file is on your computer. If you're doing IPython notebook stuff, which is not that important right now, you're going to need those items. IPython is the required. The other two are for the pretty visuals. And once again, we're going to be adding more notebooks as the thing as the tutorial happens. And what I found too is I got a recommendation to just dump the code from IPython from the notebook into like a .py file. So that'll happen too. So you don't need, essentially you won't need IPython.
Can you export the IPython before you show it to us? We can have it on our screen too.
We don't have all these set up as IPython notebooks.
But like the one you showed us before.
Yeah, yeah, I have.
There's nothing in the notebooks folder. It'd just be nice to have it on my screen.
So this one was added. And then I have, there's no back button here.
Sorry, I was looking at my
No problem. Yeah, some of these have just been updated. There is going to be a new folder that I'm going to be adding soon, which is just going to be like demo code, which is basically going to be code dumped into a demo, like a .py file to run through in a Python interpreter. I'm also have built out a VM. I'm putting the finishing touches on it. If any of you guys had like complete issues getting set up, if you don't have VirtualBox, download VirtualBox and you'll be able to open up this VM image and all the libraries will be installed. The repo will be there. It'll all be set up. I'll add it to the repo here. And then that way you can sort of interact with some of the stuff and not have to worry about the installs on your own machines. Obviously, if you're going to do this long term, you should learn how to do it on your own equipment. So.
Can you repeat the tip for Matplotlib?
Yes. It is located right here on this link. And I wanted to connect to the link because it's different for, it's different depending on whether you have a Mac or PC. I think almost everyone here has a Mac, and so specific to Mac, if you go to the GitHub repo for matplotlib, there's right in the main directory, there's a readme.osx, which contains the specific information for installing matplotlib, which basically you're just wanting to do the brew install, those two files, or port install, the same things, and then you're then moving forward with setting up matplotlib in Python. Any other questions for now?
And as you're doing this, just remind yourself that roughly in the time that it's taking you to do that, you could have been installing VirtualBox with Linux, and then it's just a clean package. And I do want to announce that I apologize for we screwed up the repo a little bit, and history will be rewritten soon, so you'll just have to recheck out the whole thing again. I'm sorry.
It's a lot smaller now, though,
yeah.
And we'll be creating a separate repo with that data file just in case somebody doesn't have it or needs it in a future reference, and then I'll create a link from our repo to that repo. So when you check out the repo, you check out the link. You don't check out the whole data file unless you want it. I will let you get back to your break now.
I did the homebrew thing work.
Okay, good.
And then the installing retype and libd.
Okay.
And I was able to install matplotlib. So you just install them from the... Yeah, after I did the brew thing, yeah, then easy install of the matplotlib from the thumb drive was fine.
Great. Awesome. Is this yours?
No, it's step 5 is
I'll make an announcement. Thank you so much. I got a black thumb drive that is not ours. A little round circle on it. No? Okay. That was great. Oh, wait. Oh, this is yours. Okay. The repository. If you look at here, so it's right there.
Guys, I brought you coffee and muffins.
Oh, thank you. Alex got more water.
Oh, well, it should be a little bit. That your words will be for sushi.
And then tonight I go to gym. By the way, the hotel gym has chilled towels. It makes you want to go to the gym. After I worked out, I got a chilled towel, went back to my room, and just like dropped my feet on it. It's beautiful. And they also, you can surf the internet while you're like doing the elliptical and it tracks everything and you're keeping it on time.
What? It's your workout?
You can tweet while working out.
No,
In the hotel gym.
but would it tweet
Your workout? Yeah, you can probably, I would not be surprised if it did. The only problem is like you're bouncing, right? So you're like, like.
No, that's why I'm saying
It's hard to.
It's like Siri. Yeah.
Tweet my workout.
Yeah, tweet my heart rate.
Can you use Twitter for telemetry?
No, so a friend of mine just published a paper called Twitter is an environmental sensor. We have all those smartphones, so it actually takes. It doesn't take very much. So like you know you can use your iPhone as a seismograph. And there is an app that if you have the app running, and there is an earthquake, it will tweet out the magnitude that it sends. So not everybody is running the app, of course, but I'm sure in California there's fair bit of people, so you're going to have decent coverage.
With the lots of people, you could do fairly nice things to reduce the noise.
Exactly.
So then what's not very sensitive, even if you're very low order bits.
Nope.
That's not what we're doing.
Well, and also quantity is one of the things that probably crowdsourcing uses. Quantity tends to correct for self-reporting biases. So even if you just ask people to write in what they felt, you will be able to see, sort of, it will cluster.
Will it cluster? You don't get sample bias based on what people write in? It seems like they'll tell me more right in.
Well, yeah, so
What is it? Yeah, you have to install it. Wait, what's the? No, just the dependencies. So you should be able to install
Normally you can do fairly difficult filtering techniques, it's where there's
So try that.
changes, so, but it's really hard to do that.
Do you open up the Python interpreter and try to import it?
yeah, but like we have amazing sensors now. Talking about sensor networks, we have.
No, I'm trying to.
I was actually just talking to some near military guys, and they're talking about how they just started doing this in Afghanistan. They just started giving the reentry response to the soldiers. And the phones run on their open network. There is a 3G network that's being built up in Afghanistan. So they have decent data coverage all over the place. So now they've been basically given the reentry response and tablets to the soldiers, and they're starting to get huge amounts of data. And it's just background data. It doesn't have to run on a classified network. But you put it together, if you know what to look for, put it together, you get some this information.
I think will be very interesting is when the major gets like glass. And it's actually a very still step around the camera on top of the rifle, so we can see very.
Yeah, they already have cameras on top of rifles.
They do. But with fairly cumbersome heads-up displays.
Yeah, so one of the things you could do is drive one of the robots with Google Glass or the Big Dog. You know what I'm saying, Big Dog.
Yeah, I know both of those. Both of those are local startups, so.
What? No, Big Dog. I think Big Dog is out of Cambridge now.
Yes, General Dynamics.
Yeah.
They're local.
Oh, that's right. You're local in Boston. That's
yes, and I know about is Rod Brooks, who was direct from CISO for a while. So.
Yeah. No. So Rod Brooks is. One of the people that is probably responsible for making me into
really?
Yeah, he's probably one of the most influential people in my life. Despite I've only met him like twice, but still. So the papers that sort of got into notoriety, right? Robust layered control for mobile robots.
I like a lot of his early work.
Yeah. So I read that paper and I used it to build a stock trader. So I was thinking about the illusions in the stock market. And so I built an illusional trader. This was not even trying to do anything about fundamentals. All it did was trade on emotions. If it felt fear, it would sell. If it felt excitement, it would buy. If it felt blah, it would, so that type of thing. So we had sort of just a five-way emotional spectrum, but it was all built on, Rod Brooks' architecture. It was purely reactive. It did really well on CAD data. I was training parameters, training the emotional engine. Did really well on that. Then I gave it about $5,000 of my own money and
Somebody
immediately
says
lost
they
it.
need a G Fortran.
Oh, no.
Fortran?
Yeah.
Oh,
So it's trying to compile it from scratch.
No, he's never installed like NumPy on his machine. And
You want to install distribution.
It will take a long time.
No, you want to install.
Can I go without NetworkX?
You're not going to get any graphics.
You can print it. But I can still use it.
Yeah, you can still not use NetworkX, but you're not.
did you update that?
Yeah.
You won't be able to plot things. But no, what you should do is install it, that thought distribution will come with everything precompiled. Free, and then you do pip install NetworkX on that, and you'll go set. It'll take you a lot less time than figuring out the compile problem. Okay, so let's. I think we need to restart, okay? Time?
Go grab my card.
Yeah, we need to start.
We could grab dinner.
Yeah, you know, let's do dinner tomorrow. Yes, there's.
Yeah.
We just deleted the big file from the repo, so you should be able to refresh it faster. And we'll find a way to get it to you again somehow if you haven't got it from the Dunbar yet. We won't put it back in the repo.
Can I get an error if I try to load the notebook into IPython?
Well, what?
Complains about truth not being defined.
True?
Oh, okay, we had that error before. You need to.
Define true as false?
No, you need a CD inside the notebooks folder. And then when you run the notebook, you need to run IPython notebook --pylab.
What?
Inside.
Tomorrow in particular will be very tight.
Okay.
It's in the readme
Yeah,
of the
tomorrow is tight
GitHub
for me as
page.
well. But yeah, so let's, yeah, and we already have dinner plans for today. So, cool, let's, you know
How
what?
long are you in town for?
I'm in town till Monday.
Okay.
And
That gives plenty of time.
yeah, so, you know, in the worst case, I mean, I'm gonna be spending a lot of time dealing with my startup stuff, but,
Saturday and Sunday both work very well.
yeah, Saturday and Sunday work, and when are you leaving back for Boston?
Tuesday night, so.
Okay, cool. And the other thing is, I'd love to come up to Boston at some point.
That'd be great.
Yeah, I love Boston. I have lots of friends there, so like, you know, I have a place to crash, all of that.
Okay.
Cool. So yeah, I'll email you after this, and we'll set this up. Okay.
Yeah, tell me the files on that.
Same error. I'm in the notebook.
No, don't do it on my machine.
No, I won't do it. Oh, I thought that meant like the name of the thing.
Later. It doesn't matter. Okay. Okay, checking the mic.
Oh, and it's just listening to the ones that are in. Okay, so it feels weird. I can run IPython. Wow. Interaction.
Yeah.
Look at this.
So to actually run these,
Look.
you want to do the, you want to
So shift return lets you keep it. Oh, right.
So if you go back to the
Now imagine throwing that in.
Yes, this is right, because I went right back.
Yeah, so it's a little tricky, but,
Yeah,
you know,
yeah.
just to kind of give you
Right.
an overview.
Yeah, it's kind of like, you know how you have the key that flips your picture into the, flips the colors in your picture.
Yep.
This is kind of.
Yep.
Right.
Okay. Open up some stuff. And Max was amused.
I didn't know that. Oh, you said it the other way, okay. Okay, I didn't realize that, yeah.
You can change one thing, it's not.
Because that's what I look back at. Because that's what I do. I try to change true to false and false to true. That's totally good.
Okay, cool. So, you think they're set to start, to restart again? Yes, everybody, yeah. Well, yeah, I think time-wise. So I want to show you some stuff we can do with Twitter. One of the reasons we deal with Twitter a lot is well, first of all, it's there. You know, why do we climb the mountain? The mountain is there. But the other thing is, it's probably the most readily available sort of bird's eye view of what's happening in the world. It's not very detailed. It's very hard to get in the weeds and really understand. If nothing else, you have huge selection bias. You know, the entire middle of the United States is horribly underrepresented on Twitter. If you pull Twitter data, it's going to be the East Coast, the West Coast, and maybe like a little bit down the Mississippi River Valley. So we'll have Chicago and Minneapolis and St. Louis and a few other big cities show up. And then there are big blank spots where, you know, all of the non-urban people live. And it's really not, you know, not what you want to know when you're trying to understand what's happening in the country. But as you know, as broadband starts penetrating, what you get, it's more and more these days, is that the density of Twitter activity it becomes proportional to the density of people living in the area. So it's now getting closer and closer to being sort of a representative gauge of what's happening in the world. So and Twitter itself is not a source of content. To me, Twitter is the wire. It's sort of the APIs that you use to transmit other things through it. And the other thing is it's very real time. So if you want to know what's happening right now and you want that data right now, it's awesome. So the other thing is Twitter is very rich. So believe it or not, it's you know, with 140 characters, we can actually get a lot of stuff out of it. We have some idea of how we can get the trust and influence. We have some idea of how we can get an information diffusion. You know, how are things spreading through the network? We can talk about language. We can talk about some semantics. Not so much, but some. Stuff like this. It's actually incredibly powerful for just having 140 characters. One of the examples that we've seen is Twitter being used as an environmental sensor. If there is an earthquake, everybody tweets about the earthquake. The funny part, I actually did this analysis. There was a huge, horrible earthquake in Virginia. Yeah, 3-pointer. You know, yeah, everybody who lives in California should laugh at this point. 4, sorry. Yeah, fine. Yeah. So, but the funny bit was, so everybody who has never lived in California started hiding under and running out of the building. I was like, it's a 3-pointer. So I was like, okay, I'm going to start a Twitter collector instead. So I grabbed some data, basically, in a few seconds after I felt the earthquake. What I did then is I measured. So I geocoded all of the tweets based on reported location or based on somebody's location of their cell phone. And I looked at how fast the information spreads. And guess what? The information about the earthquake spread faster than the earthquake. So the speed of the shock wave in the ground is, last time I checked, it was 8 kilometers a second or something like this. So it's pretty damn fast. Well, people in New Hampshire that actually also felt the earthquake had the epicenter in like southern Virginia. People as far as New Hampshire and Canada felt it. Well, they had about 30 seconds warning, because they have seen the information and they have retweeted it before they felt the earthquake. Of course, they wasted that 30 seconds warning on retweeting. So, it wasn't really useful. But it was very interesting to see how this works as an environmental sensor. It can be used as a pollution sensor. A friend of mine is actually working on this, looking at people reporting smog and pollution in LA through Twitter, and then trying to compare this to actual data that's being gathered by air quality monitoring stations. And it's actually quite good. So you can monitor epidemics, you can monitor the flu. All you need to do is you need to geocode when people say I'm feeling sick. That will give you an approximation of where the flu epidemic is going. There's pretty high degree of accuracy geospatially. So, but before we get to that, we have friends and followers is sort of our standard. The first thing we look at, and it's something I actually stopped looking at because I found this rather useless. So clicking the follow button. Remember how we're talking about emotional energy invested in a relationship. When you click a follow button, you've invested 0.1 second of your life into clicking that button. Whether or not you will ever read anything I tweet is another story. Probably not. Especially if you have 8,000 Twitter followers, or if you follow 8,000 people. So a two-way relationship. I follow you, you follow me, is much better. That means we actually know something about each other. We've invested some time into figuring out who each other is. But what I found is if you wanted to look at trust, if you wanted to look at where the information is likely to spread, that who is likely to follow something or react to something you say, you need to look at retweets. So if I retweet you once, well, that's something. That means I at least read what you tweet. It's worth something, a little bit. But if I retweet you many times and you retweet me many times over time, we can actually track that. And we can look at the trajectory of the relationship and see, okay, here's two people meeting. They first followed each other on Twitter, and now we see a growth in mutual retweets. There is some idea of where the relationship is, and potentially the relationship wanes, or, well, in my case, one person just stops logging into Twitter because they get bored with it. But at the very least, you can actually see the trajectories. And the other thing that happens here is, and this part is, by the way, awesome. So Twitter has a 1% feed, the sample stream. And a lot of people just use it for testing their software because it's rather worthless if you just do it for a little bit. What we've done, and Alex written most of that code actually, is sample that stream for over a year. How big was our database? It had like 650 million tweets.
It was 1% stream was roughly about 1.5 million tweets a day.
Yeah.
Back when we were doing this, probably
Yeah.
more.
Right. So after a year, I remember we had over 600 million tweets, and we had something like 30 or 40 million profiles. This was a serious amount of knowledge about the world. It presents a very bird's eye view picture. It doesn't give you a good understanding of detail, but if I want to know, approximately what were people talking about in relation to wombats or anteaters, big random things that people generally don't talk about. Well, there is something. We'll have at least 1 or 2 tweets about wombats. So it was awesome because you could just dig in and see what else are people talking in connection to obscure topic X. You get a really big picture. Who is talking about it becomes secondary and actually rather low fidelity because you only have 1% chance of capturing any single person. But also the accumulating 20 to 30 million profiles That's worth something. That's, you can search in that and you can get a lot of information. So I urge you all of you to explore doing this and start your own 1% collector and have it hanging out and dumping stuff into a database. It will let you learn more about this stuff than you've ever done, and you're actually going to learn something about the universe. So seriously, this is pretty cool. So okay, so Twitter for networks. Let's just. I want to tell you how. Yes.
Is it worth saying how easy it is to set up a collector?
Yes, I will show you. It takes. You know how many lines it now takes?
Well, I've got one whole line.
One. Yep. It's a. Yeah, I'll show you this. It is. What I do is a little bit more. It is a little bit more involved because I build networks from it. But if all you want to do is read it and, let's say, dump it to S3, it takes one line. So, okay, so here's a tweet. Alice said that she retweets from Bob, who mentions Carol, who just felt an earthquake in Fairfax, Virginia. So what that means. So remember how we described nodes and edges? Nodes are nouns. Edges are verbs. So Alice has retweeted from Bob. That's edge number 1 with 2 nodes. Bob has mentioned Carol. That's edge number 2. And also, hashtags earthquake and Fairfax are related. And also, Carol felt an earthquake in Fairfax, therefore she must be in Fairfax, so we can have that relationship. So you see, we're starting to extract all of this stuff. If we just have this one tweet, it's not much. Imagine we have hundreds of thousands of this. You're starting to get the picture. You're starting to you're starting to figure out. You will know where the earthquake has been because people have tweeted about the earthquake from different locations. You will know how the information spreads because you will see who retweets from whom and in what direction. So you get all kinds of stuff. So yes, as I like to say, so one tweet can only contain a handful. Tweets as a corpus can tell a huge story. So you can get a lot of stuff. So collection. And I have the files in GitHub. In the Twitter directory, so you can do it yourself. The library I use is called TweetStream. So this is you need to pip install TweetStream, and then you say for tweet in stream print tweet. Well, that's just getting the data. And you can do so here I'm setting up a filter stream where it's tracking some people and some words. Let me actually show you. So we're gonna go in here. It's GitHub here. So if you go into source and Twitter and look at collector, so actually so I just modified this to look at the Pope because we just had a new Pope has been just elected. Up. Oh, shoot. Like this. That's better. Yeah. So we import tweet stream. There is a little utilities file that I use that is very useful. I showed you this one that has all of the trimming commands. So we're looking for hashtag Pope. And we're going to gather the retweet network and the hashtag network. So okay, so the first thing we're doing is we're setting up the stream. And there is a username and a password, and I'm about to burn this password because I'm showing it to everybody. So we need to remember to change it afterwards. But it needs valid credentials, and you also need to authorize the app on Twitter. Otherwise, it will not let you have the data. But once you do it, you can start streaming. So let me just show you.
Which one is the app?
I'm sorry?
What app did you have to authorize? Using this library, you could be writing many apps.
Right, right. Well, so what you need to do is go and you don't need to do like full app authorization. You just need to authorize an app, and then to those credentials, and then you'll be able to get the data. Because otherwise, it will not let you run the API. So I'm just going to grab this for print. For T in print T. Shoot, sorry. Words. Okay. There we go. So data is streaming. And then I killed it. Okay, so now, so what are we going to do here? Well, the first part here, we just extract. So we extract the entity, the author. We extract all of the mentions. So this is who was retweeted from or who retweeted it. And we also extract the hashtags. We add edges for retweets.add edge here. And we also create a hashtag network. So here there is this little function that I use. This is part of my utilities package, add or increment edge. So this will create a valued graph. So for every time an interaction repeats, that number it increments a counter. So that lets us cut down the networks. It enables the trimming. So let's run this for a little bit. And I'm just going to leave it for, I don't know, for a few minutes. Let it collect data. This is one of the biggest trends in hashtags right now, so it's going to get a lot of data very quickly. And then we'll be able to see what are people talking about in conjunction with the election of the Pope. Oh, connection error. So this network is a little flaky, so things will get dumped. Well, what did we get? No, what happens is Twitter will drop connections. If there is any kind of hiccup in the network, Twitter will drop the connection. You have to reopen it. Yeah.
Are there any services that will collect Twitter data
yes.
for you?
Yeah, funny that you ask. There are two companies that have been blessed with the official Twitter fire hose and resell it for a small fortune. There is one called GNIP. That's pink spelled backwards. So GNIP will get you either a filtered fire hose or it will get you various search and follow collectors for about $2,500 a month. Yeah, it's a little bit of money. The other one is called DataSift. It's a British company. They have a very nice pay-as-you-go plan that only runs, say, about $100 a week. So for a consultant client who is flush with money, it's not a big deal. But yeah, for fun, you have to do it yourself.
I mean, obviously, the full fire hose is a massive amount of data.
Yes.
I'm more thinking of like a subset of tags or
Mhm.
something like that.
Yeah, well, yes, exactly. You can set up a collector there that what DataSift does is they calculate how many computing hours you have used up, and they will actually drop data for you in JSON format on S3. Yeah, so it's pretty nice. In my cases, you know, it usually ends up costing about somewhere between $100 and $300 a week for, you know, reasonably large size collectors for commercial clients.
So I haven't used Knip, but I use DataSift
Mhm.
with my clients, and there one of the nice things is you can go back in time. So you
Yeah.
can give it the hashtag and the date range, and then buy as much data as you want in that range.
Yeah, yes. You can do the same with GNIP. It's a little bit of pain in the butt. GNIP, actually, so you know, and anybody from GNIP in this room? No? Okay. And anybody from DataSift? No. So, okay, DataSift, in my experience, is significantly less pain in the ass than GNIP. For close to order of magnitude less pain in the ass. And also less money. So, at this point, I have become a convert. Yeah, Alex knows all about the pain of, because he's built all of those collectors. Yeah, keeping connections alive, things like that. Yeah, so, but for 1%, all you need to do is you run that feed, you watch for a dropped connection, and you open the connection. So it takes a few lines. But let's see what we got. Oh, sorry, Len, retweets. So, well, didn't get very much retweets, hashtag, net, Tom. Nah, not much. We need to, I want to rerun this. Get some more. See how long it takes until it dumps us again. Yeah, this network is flaky. It's going to get dropped. Up. One more time. But you get the picture. If you're on a good, no, this is not going to work very well. Yeah, we're not getting good reception on this. Oh well, I have some canned data. So what happens with this is when we load the data, and we just need to run through those tweets and create hashtag networks and create retweet networks, and then we can analyze them. And there is a canned data set in your, actually no, it was corrupted, right?
Yeah, it was on the jump drive.
Ah, okay, it was on the jump drive, but not on GitHub.
Does anyone need a copy?
Okay, yeah, so there is a 200 megabyte data set from the earthquake, and you can grab that and play with it, and it's really the same thing. So, you know, when yeah, so here, okay, so yeah, so we're going to collect retweet networks and map out information diffusion. Okay. So actually, yes, we talked about all of this stuff already. I showed you this. Okay, so this hashtag. Hashtags are really cool. They're free form. You just sort of dump it in when you're writing, but then you can search by hashtags. It becomes an index. And what happens with hashtags is you actually tell Twitter what you want people to search for. So you're actually expressing something about your own, about the semantics of what you're about to say. So that is really cool because you know, instead of doing latent semantic analysis or trying to infer the meaning from what people are saying from the text, well, people can tell us. You know, so we just use. All we need to do is map it out and see what happens. So yeah, so we basically do a value graph. So when two hashtags occur many times together, it signals that there is a real semantic connection. If it only occurs once, it's probably chance. If it's only, or on a large enough set, I might trim it to say, okay, if it occurs less than 10 times, it's probably chance. No? Got a question? No. Oh, okay. Yeah. So so we create a valued graph. All of this code is checked in. It's actually going to be easier to read than. So as a result, this becomes our hash. So we get something like this for a hashtag network. So we have a giant hairball in the middle, and sort of smaller groups of little hairballs on the outside. So we want to get rid of all of the outside stuff. All of the outside stuff is noise. So we use connected component subgraph. So that's the thing I showed you earlier today. We use connected component subgraph, and we grab the largest connected component. By the way, the useful thing about this function, connected component subgraphs, is it returns you the subgraphs in order of size. So if you grab the component 0, you will always have the largest one. And if you look at the distribution of sizes, what you're getting is, so let's say the largest component here is a few thousand nodes, and the next one is going to be like 100, and the next one is going to be 20, and then it gets down to 1s and 2s very quickly. So one of the things that I like to do with this, so here this was all about the earthquake. This is from the earthquake data that is on thumb drive. So the next thing I like to do is delete the central part. So so we take this, really hairballish, and take out the word earthquake. Why do we do that? Well, we know that all of those things share that one central word. And what we want to know is what other things are people talking about in conjunction with the earthquake, or with the central topic. If we had data on the Pope, I would delete Pope at this point. And by dropping this, I'm basically starting to see the structure. So we can see that there are clusters that are emerging all over the place. We can study each one of those clusters separately. We can trim up the edges a little bit. So here we trimmed on weight of 2. Yeah, apocalypse. Yes, that's how scared people were. They were looking for zombies in the street. Well, here I trimmed it up even more. So check this out. There is a cluster down here, somewhere down here. It's still pretty well tied in. Oh, by the way, Tea Party had something to say about the earthquake too. I don't know why. Probably because the earthquake was a liberal, so it was caused by the overly permissive liberal attitudes that led to the election of godless socialist Muslim Obama. I don't know, whatever. Yeah, so, but anyway, so if we trim it up a little more, the Tea Party falls out, and the spammers fall out. So this one is, Team Follow Back is a curious spam group. So let's say you wanted to suddenly have 10,000 more followers on Twitter. All you need to do is go and follow Team Follow Back, and you will start receiving spam in your Twitter account. Through that you subscribe to spam, but in process you're going to get everybody else who follows Team Follow Back will follow you. So basically you increase the amount of noise, but you can game this. Your cloud score goes through the roof if you do that. If you care about your cloud score. But I think cloud is getting smarter to that. So anyways, those guys are all over the place. Getting rid of them is very easy in the data. So what would I do with this? Well, sometimes I want to know what the taxonomy of event is. So what I care about is what are the terms that are surrounding the term I'm interested in. So as I was shown in case of Egypt, and I was able to see what is semantically what is the relationship between, let's say, Egypt and Tunisia, and the revolution in both places. One of the sort of bigger studies I've done was looking at Islamist language in the tweets, and basically mapping out how the Muslim Brotherhood started. The revolution in Egypt started out was started by the liberals and was very quickly taken over by the Muslim Brotherhood. And you could actually map this out. You could see how the Islamist language emerges and talk of morality and things like this. So instead, you start with words like freedom and things like that, and suddenly there is morality and Sharia and things like this. So you can see how the language changes, especially if you look at this over time. So to me, this is as good as latent semantic analysis. I think it's actually better because it's much easier to do, and it scales much better. I've done this type of analysis on easily hundreds of thousands of nodes, or running against a multi-million tweet database, no problem. So here's the other thing to do, and I did not provide the geocoder in the GitHub. We can actually drop it in. I have a little geocoder that takes Twitter location data is garbage. It's in 4 different places. It's really badly encoded. Sometimes not encoded at all. So I have a geocoder. I'll throw it into the GitHub. That I use a modified version of GeoPy, and it goes against the Yahoo API and collects all of the possible typos, every possible garbage that can happen with geospatial data on Twitter. And if you call it, you just get location. It's a JSON object. And you create this. So one of the things I've done with this was create a spatial graph. So this one is linking locations to tweets or locations to concepts. So here I had locations to hashtags. So I wanted to see if, in this case, I was looking at Obama versus Romney right before the election. I wanted to see which parts of the country used more Obama hashtags versus the Romney hashtags. Do we have a? Oh, yeah. I don't have a picture of the map here. I'll have to pull that out separately. Yeah, for retweets, we get something like this. Again, this is a big, giant hairball. So this. This consists of a lot of pairs. I retweet from you, you retweet from me. So the first thing we do is we, again, same thing, connected component subgraphs, very easy. And in here we get things like this. Each one of those is a cascade. So this is, if you look at this in time, what you're going to see is there is a single source of the source of information. Let's say this guy tweets something out, and it gets some response. It gets a reception, and then Lavora Stiletto gets and retweets it, and suddenly it creates a whole new cluster. And if you look at this over time, you can actually see how this thing evolves. So for that, you're going to need to slice your network into times, but you can see how information spreads over time, and this is pretty amazing because you can now see how Twitter reacts, how the universe reacts to events. So each of the cluster represents an information cascade, and if you want to know who's been most influential in this, all we need to do actually is just do degree. So again, we originally talked about degree as number of followers. Number of followers is not necessarily a good metric, but degree in a retweet network, we're not looking at, you know, somebody who clicked once. We're looking at somebody who actually read and understood and decided that it's worth repeating. And presumably, because we've already cut it down a little bit, something worth reading and repeating several times. So high degree nodes are going to be the ones that cause the most retweets. So if, what you get from this is, you know, people who have in the past wielded influence on a certain topic. So if you look at the top 10 people or top 100 people, those are real influencers. Those are people that have really said something that have moved the discourse. That's pretty cool. I know of a number of large marketing companies that paid real money for this, and we actually built a consulting company around it, more or less this idea, plus a few other things. Yeah, and this is what the degree distribution, by the way, looks like. So if you did a histogram, you get most people, you know, that's the periphery. Most people only have one retweet. But then we have people in, you know, there's one or two or half a dozen in the 600 range. And so that's where the influences are. Okay, so if we wanted to know who is at the core of the network, there is a function in the utils folder that I've given you called trim degrees. So what that's going to do is remove, I think I showed this on Congress before, it will remove everybody with degree of 1. You can rerun it multiple times to get more of the dangling pictures here, or the dangling nodes. So you see, you occasionally have this long chains. If you run trim degrees multiple times, it will gradually remove them. From something, so yeah, this is kind of hard to see, but you can actually start to see clusters inside this network. If you did the degree and you sorted this, you're going to get, yeah, Lord Voldemort was for some reason highly influential in the presidential election stuff. I don't know why. And Darth Vader and CNN, well, CNN breaking news, we know why. If we did so we can do other things. If we did betweenness on this, betweenness will show you people that are spanning boundaries between different communities. The other thing we can do with this is clustering. So Jackie, how are we doing on time? 40 minutes, perfect. I'm running straight on schedule like a train. So clustering is really, 1 second, I need to reopen a couple files. Okay. So I have, there's a few ways of doing this. There's a few ways of clustering networks. What I'm going to show you is a method that uses hierarchical clustering. Actually, there is a file checked in that gives you all of the code for free. You can play with it. It's incredibly powerful. You can throw a huge network into it, and you're going to get it's going to get cut very nicely into communities. The only unfortunate bit about that is hierarchical clustering is a bit slow. So you want to do all of the other things before you hit it. You want to cut it up into separate components. You want to remove the peripheral nodes, et cetera, et cetera, et cetera. So the fewer nodes you throw into the clustering algorithm, the faster it's going to run by an order of magnitude. So, okay. So give me 1 second to set this up. So I'm going to use a different data set with this. This is data I obtained from, has anyone ever used PubMed? No? Yeah. So PubMed is a huge database of medical research. Well, not just medical, actually. They now have anthropological, sociological, and even some computer science work. But it started out originally with medical research. There is a set of functions enclosed in the repo that will go to PubMed and get articles. I'm not going to do it now because of our network, but we have this file, so articles.json.zip. I just unzipped it, and it's about 6,000 articles related to research on ADHD. And well, frankly, I stole it from one of my recent consulting projects, but it's public data. So PubMed.py will get all of the data for you. So there's a function called get articles. Then the make author network will create a network here. And let me open this up. And community community.py is the community detection algorithm that that you can use. So let's see. Okay. And okay. It's not going to work that way. Okay. So okay, there we go. This will require one package that was not on the flash sticks. The package is called BioPython. So to do that, you're going to need to, in your terminal, say sudo on a Mac pip install BioPython. Yeah, so you already have that. If you don't get BioPython, you can work with canned data with the JSON file. But if you want to run the queries against it, you're going to need it installed. If you want, PubMed is actually an amazing source of data because it tells you everything about science. You want to know how medical science changed from 1950s to now. That is the kind of data you can get. You want to, one of the things that I've done is, this was a non-profit project. A very well-known institution in science they want to enhance their interdisciplinary collaboration, blah blah, getting scientists in the medical fields to work with scientists in non-medical fields, and they were investing serious amounts of money into it. And I was hired to look at their data and to see if the people are actually collaborating the way they want to be. The administration wants them to collaborate. And we found actually some unpleasant news because collaboration across the fields was pretty much non-existent. Only a couple people did it. Everybody still was pigeonholing themselves in their own field. So they had to do something about it. Okay, let's see. There we go. So well, let's see what else are we gonna need. So we're going to import utils. So CD to the directory. And there's import PubMed. If you don't have BioPython, that's not going to work. So we also need to import utils. Community file, community detection, and as always, NetworkX. So the first thing I'm going to do is I'm going to load the articles. And this is just loading them from, and by the way, all of this is in tutorial.py. So all of those lines of code. So this will just read the JSON file. 6,400 articles. A lot of biological articles are co-authored by large numbers of people. We can have sometimes 20 people in an article. What we're going to do is we're going to create a collaboration network. I'll show you this function. Yeah. So all that we do here is we iterate through the articles in the article list. We grab the list of authors. Now, has anyone ever used the itertool package in the Python standard library? It's awesome. You should use it. So permutations will basically generate every possible pair of authors in a list of authors, and we could have easily 20, 30 authors in there. We call this, so add or increment edge from the utilities package on every pair. So, and that will generate the network. So let me just do this. And that will get me my co-authorship network. Oh, that was quick. $13,736. So we have about 14,000 people that have written articles on ADHD in the last 5 years. It's a pretty big field. So I'm going to trim it as we have already done this. So I'm trimming the edges, and I'm taking connected component subgraphs. So the things that we always do. So hold on a second. No. There we go. 392 components. So okay. So here's what I've done. I've removed all of the collaborations with less than 2 papers. So that sort of gets rid of let's say students that have only done 1 or 2 papers in general. One of the things that you see in scientific networks is that some collaborations are real, and you have actual groups of people working together on a problem, and some collaborations are sort of well, there's still collaborations, but they're just not in real time. So if I went, let's say I got my master's degree at the University of Minnesota, and I wrote some papers with the professors there, and then I went and got my PhD at Carnegie Mellon, and I wrote some papers there, and I went to teach at George Mason, and I wrote a lot more papers there, etc. So if I took this record, it would seem like Carnegie Mellon is collaborating with the University of Minnesota, which actually they were separated by about 10 years. So we want to be careful about that. I usually cut it on time and also remove the smaller collaborations. But anyway, so 392 components. And I want to see what's the largest one. The largest component is 1,000 people. Perfect. So this is actually perfectly sized to be visualized. draw. So you see how long it takes to draw now for 1,000 as opposed to 500? Takes for 2,000 it will take 4 times as long. So there we go. So yes, we still have a hairball in the middle, but we're actually seeing structure. So what we're, there are peripheral groups out here. So one of the things that that we were trying to find for ADHD researchers is there are three approaches to ADHD. One is medication, one is therapy or psychotherapy, and one is what you would call lifestyle. So they're doing sports or changes in how kids are educated, things like, and trying to figure out how to get kids, how to treat ADHD without medicating kids. This something like this. I wanted to actually see if there is a sort of a line of hybrid approaches that try multiple things at the same time. Before I actually run the community detection, so we've got our data. We built the graph. So this is actually a smaller version of the same graph. Now, the next thing we're going to do. And this is not something that this is something that is done automatically by our community detector. Is we're going to compute Pearson correlation between nodes. So all that Pearson correlation is basically you're going to take person A and person B and compare who they're connected to. So we're going to treat their set of connections as a vector. And we're going to compute correlation between those two vectors. And then we're going to put this in a matrix. So this is person 1, and he has perfect correlation with itself. The person 2 has perfect correlation with himself. People 3 and 4 seem to have perfect correlation with each other. So basically your location in the matrix starts to matter. And by the way, if you thresholded this, you would also get a network. So you can interpret this matrix as a network itself. Except this time it's not going to be a network of who talks to whom or who collaborates with whom, but who is similar to whom. And through this similarity, you can see, okay, this looks like a subfield, that looks like a subfield, because people are doing similar things, or they're connected to similar people. So that's pretty cool in itself. But what we're actually going to do is hierarchical clustering. So we start with the Pearson correlation. We can actually have a lot of other distance matrices. I'm not going to talk through that. And the algorithm is very simple. And I'm not going to talk through the code for the algorithm. There are some twists and turns to getting this done right. But the algorithm the implementation is available. In the simplest way, here's what you're doing. You're going to start with all of the nodes in the same cluster, on the same level. And that's, each node in its own cluster. And that's perfectly useless. But it's actually mathematically correct. What you're going to do then is you're going to merge, you're going to take the two nodes that are most similar to each other, and you'll merge them into a cluster. And then you're going to take the next two nodes that are closest to each other and merge them into a cluster. And you're going to basically keep doing this until you merge everything up into one big cluster. So the bottom result with everybody in their own cluster is useless. The top result is everybody in one cluster is completely useless. Something in the middle is really good. And that's the thing we're looking for. So the algorithm that I'm giving you actually has a way to tune how it clusters things. And it will get you, with the default parameters, it will get you very nice results. So I want to show you how this works on, basically BS piece of data. So this is using, it's called single link clustering. So single link means we're gonna look at the closest pairs. So we have 9 cities in the U.S: Boston, New York, D.C., Miami, Chicago, Seattle, San Francisco, LA, Denver, and we want to cluster them and see if we can emerge concepts of East Coast and West Coast and Midwest. It's a simple example to try on. So Boston and New York merge in the cluster right away. Then Boston, New York, DC. Then things get funny. So San Francisco, LA, Seattle get merged into a cluster. The next closest thing that happens is Chicago. So Chicago gets added to the East Coast. This is where all of the good algorithms should stop. Because they're now basically pulling stuff by its ears. Chicago should not be with the East Coast. But we continue until we get to the bottom and useless result, which is all of the cities except Miami are in the same cluster together, and Miami is too far away from everybody. So the bottom part emerges the concept of north and south. But somewhere at this level, we actually get into good groupings. So we know Boston, New York, we have the East Coast, we have the West Coast, we have the South, here only represented by Miami, and we have Denver as, I guess, the mountains. I'm not sure what Colorado is counts as this region. And if we were to look at this in terms of level, so people talk about this in terms of levels. So here, everybody is in its own cluster, and here everybody is in the same cluster. So when we find an optimal level here, that's where we're going to get useful information out of this. So let me actually run this for you. So what we're going to do is we're going to derive a partition. And community.best partition. So this is a dict, and what you have here is so name of the person and number of the clusters that he's been assigned to. The clusters are just they're numbered, they're not labeled. And we can look at the lists for if you want to derive a list for every cluster, you would say something like if v equals 10. So yeah, there we go. So okay, so this line here, it gives me people that belong to cluster number 10. So I just did a quick list comprehension with this. So that's pretty cool. We've clustered them. What else can we do with this? Well, the next part is actually is much cooler. We can now generate. So we know who belongs to each partition. Let's now generate their networks. How are they connected to each other? So and for that, I actually have a helper function. So community.plot partitions. It wants a file name. Part. Okay, takes a while because what it's actually doing is there we go. It's actually generating images. So this is all hard-coded for you. And if you look by numbers, so this is partition 0, partition 1, partition 2, partition 3, 4, 5, etc. I've turned off the labels to make the images a little easier to see. If you turn the labels back on, what you're going to see is, for example, SUNY Buffalo. There is a cluster that's dedicated to SUNY Buffalo. And so it actually figured out that, yes, this university has a good psychiatric institute that does a lot of ADHD research. And here's a separate cluster for them. Here's a cluster for NYU. Here's a cluster for Canada. There is a lot of things going on in Canada. There is actually a lot more collaborations going on in Canada. So it actually, once you look at the cluster, you actually start seeing the stories. What's going on here? How is you can see the Ivy Leagues, for example. There is another, or you see one of the divisions you're going to see is people who only deal with drug-based treatments and people that are only dealing with psychotherapy-based treatments. So things like that. So it starts cutting the data into pieces, and each one of them is a relatively small piece. It doesn't take a long time to compute, and you can get very powerful interpretations. So I want to do something else here. Yes. So there is another concept here. It's called the induced graph. So what we did here, we took this large network and we cut it up into pieces. But in process, we're losing how the pieces are connected to each other. Well, with this function, the induced graph function, we're going to reconnect them back together. So the induced graph is, I'm going to draw it. So the original graph had over 1,000 nodes. This one only has 32. What the nodes here represent are groups. So the community detection algorithm has found our clusters. Now we want to find out how the clusters are related to each other. Which of those clusters, which of those groups are more central? Well, that's a network. So I'm going to draw it for you. Oh. Yes. Oh. Hold on. Something's funny with the resolution. There we go, that's better. Okay. So something like this. So this is now much easier to read, except each one of those nodes actually represents a couple hundred people. Well, actually, probably a little less than that. So now you see that like community 0 has, hold on a second, I need to redraw this. So community 0, for example, is very central. And you can actually do the, oh, that's what happened. It opened up all of the pictures that I generated before it opened all of them up, and there were 30-some pictures there. That's why it was off. Let's redraw this. That's much better. There we go. Yeah. So you see that that group 0 is very is very prominent. And you can also see like group 20, for example, is interesting, and group 2 is interesting. Well, let's see if we can. Let's see in this who is in group 0. So this also generates a list in CSV. Okay, there we go. So I happen to know who those doctors are. Dr. Greenhill, the third guy in this list, he's actually one of the most prominent psychiatrists in the United States. One of the most well-published ones. He runs a center at NYU. Yeah, actually there is also a misspelling. There is Dr. Swans and Dr. Greenhill. They have been misspelled twice. So they also show up in the same cluster. So I happen to know that the reason those people are here is because they're like chairman of the board of the National Institute of Mental Health, things like that. So they are actually in real life, they're highly prominent people. Here they're highly prominent in their own cluster, and their cluster is highly prominent. So if you use this technique on a large-scale network, you grab the clusters, you look at who is important in the clusters, you look at the importance of the cluster itself, you get a good idea of where somebody stands. One of the other things you can do with this, and this is sort of off the left field, but if you wanted to do a recommender system, so for Twitter, for example, who would you like to follow? You know, better discover tab for Twitter, something like this. Well, what you do is you take the Twitter network, you cluster it. That actually becomes a very much of a big data problem. You take the Twitter network, you cluster it, you cut it up into pieces, and then you say, okay, so Max, your Twitter account is in the cluster this group of data scientists. You happen to follow 9 out of 10. Why don't you follow this guy too? If I happen to follow everybody in my cluster, well, which cluster is the next closest one? Let me suggest some people from that cluster. So this actually lets you build a very nice recommender algorithm with not much infrastructure. For really big data problems, like this Twitter, what you're going to have to do is the Pearson correlation matrix here, the one that I will show right away, that's an n-square problem. That thing is a pain to compute. So for that, you want to write a MapReduce job and run it on a big cluster. But as much of a pain as it is, it's also embarrassingly parallel. So it can be split up across as many machines as you want to. So this is actually something that Living Social is doing. I've talked to their guys recently, and anybody from Living Social in the room? No? Living Social? There's a .com juggernaut in DC, so I think probably one of the only big tech companies to be started in DC. Well, AOL too, AOL and Living Social. But so the Living Social guys use very similar algorithms. So okay, we have 10 minutes. Okay, so I think this is actually a good time to get into questions. There is obviously a lot, I've covered a bunch of things. There is a lot more to this. I actually teach a semester course on social network analysis, and just in case you don't have a copy of my book, I have a book out. I'm shameless. I have discount coupons in my bag if you want them. But actually, you will be able to get the book on paper downstairs tomorrow during the reception and afterwards until they sell out. I don't know how many copies they're bringing. So there is a lot more to it. Feel free to ask me questions. I have cards so you can reach back to me. I can basically help I've been helping people build out this kind of stuff for a few years for their companies. So anyway, questions? Anybody? Yes, sir. The book is called Social Network Analysis for Startups. It's published by O'Reilly. I'll get it up on the screen. There we go.
You didn't find it enough.
Oh, there we go. So there's the book. So Alex and I published it last year. We actually have a second book on the way that's going to be out by hopefully sometime in the summer. So, yes?
You mentioned a lot of things that are useful for like snapshots of networks.
Right.
I wondered if you had any recommendations for tools for time series analysis.
Yeah. Yeah, so time series is unfortunately a bit underexplored these days. The only thing I've personally done with time series is so looking at cascades. So one of the dimensions, if one of the pieces of data you get from Twitter is a date or time of the message. So what you do is you label nodes or edges in the graph with time, and you can look at breadth, width, and depth, breadth, and velocity of information. So for information diffusion, this is actually extremely useful. Marketing people love it because it lets them. It basically shows how their message resonates, if it resonates. Actually, marketing people are usually unpleasantly surprised how badly their messages resonate. I've seen a lot of frowns when I show them the data. Yeah.
So when you talk about message propagation,
Mm-hmm.
talking about phrase propagation.
Well, so we can do a few things. We can track a URL. I actually have a patent on a URL tracking algorithm it's pretty cool. It uses a hack on the HTTP protocol that is ignored by everybody, except by people who know to look for that hack. It's a tag marker. So we can do that. We can track a URL. One of the things that Bitly does, and you can, by the way, you can buy Bitly data from DataSift. So one of the things that Bitly does is they will actually track a specific short URL, the 6-letter hash, as it propagates across the network. And you can actually watch that, not in real time, but almost. So you can do URLs, you can do linguistics, you can do hashtags, you can do links. So if you don't have a specific URL, you can go against an expanded URL. And sort of in general, if you can get at the concept, so with some computational linguistics, you can sometimes get at how a concept is expressed and see how well that works. Also, well, the other thing I've done is track this in conjunction with sentiment. So, let's say client X commits a public relations snafu. I want to know, how quickly does negative sentiment travel through the network, and does it ever dissipate? And so that works pretty well. So you're going to need extra outboard parts like sentiment analysis, but those are more or less off the shelf these days. Yep.
What other visualization tools other than Matplotlib?
Lots of things. So are you good at JavaScript? There is an amazing tool called D3 for JavaScript. They do network visualizations very well in the browser. Unfortunately, proper JavaScript programming still eludes my poor brain, and I have not been able to master it.
I think there's also a limit on sort of what you can effectively visualize, which should be noted.
Yeah.
Before you have to sort of come up with other ways.
Right.
I've seen the hairline visualizations.
Yeah. Yeah. There is a few interesting ones that let you. So by the one of the things that community detection lets you do is so we can take that implied graph where we have relationships between groups, Now, instead of using circles for that, we can generate an image for each one of the groups, shrink it down, and use it instead of a circle. So with that, we can visualize a much larger graph. So with Matplotlib, you have to do a little tweaking to make things look good. With Gephi, so a couple of people here, you have tried Gephi. Can do very nice looking pictures. My problem, I don't use Gephi regularly because I have managed to get it to fall on its face a few times. Your mileage may vary. And they're also consistently improving. So
I think there's a lot of research out there too on sort of handling large graphs and visualizing larger ones, and I think part of it is about sort of trying to visualize some of the components or communities and then looking at those communities individually rather than having a big hairball, which Max discussed today.
Yeah. The other things that I'm a fan of because it scales amazingly. There is an open source tool, I think it's IBM, called the Large Graph Layout, LGL. It has not been wrapped in Python yet. By the way, anybody in the room knows how to wrap C in Python? You do. Cool. You want an open source project?
Nope.
Because yeah, we have a very cool library that's probably about 5 or 6 years old. It's really mature, but not enough people use it because it's really difficult to use. You have to actually write C code to use it. So Python wrapper is in order to make it nice.
I also want to recommend the NetworkX mailing list is actually pretty good, and some of these questions come up, and people are pretty responsive with answering your questions also. That's been my experience. And they have some of these off-topic conversations, and sometimes they explicitly are like, you know what, NetworkX does not do this, it can't handle it, you should go look at these other tools. And they're really good at sort of pointing you in the right direction.
Yeah, so, and the other thing is, it really depends on, the problem. What it is that you want to see. It's not just, let's throw a hairball on the screen and look at it. It's, let's figure out how we can tell the story with it. And a lot of times the network visualization is not what you want. On occasions, actually, what you want is not even visualization. On occasion, what you want is a spreadsheet that you could sort and cut in various ways. That has been, believe it or not, with all of the time we've spent dealing with visualization, our clients still want spreadsheets. They want to be able to sort the data in various ways and figure it out, and that's what they get. 300,000 line Excel spreadsheet. Fine, have fun with it.
So
yes, sir. So not all of the algorithms are distributable, and that's sort of the problem. One of the problems with social network analysis is the field is it's not run by computer scientists. The field is run by sociologists. And there are a few computer scientists in the field, myself included. And in our copious spare time, we try to play with this kind of ideas, but it depends on how copious the spare time is. My general my general impression is the problems are either going to be embarrassingly parallel. So in this case, you can trivially write a pig job, or run something on Hadoop, or run something on PyCloud, or they're going to be not parallelizable at all. So for example, drawing the graphs, doing the graph layout, it's not parallelizable in any easy way. And between the centrality, it's difficult to parallelize as well. So it's sort of one of the two extremes. And the embarrassingly parallel ones we can take care of. The not parallelizable ones, I would say find another approach. So you figure out if you can trim things first, if you can do them one part at a time, stuff like that.
So we need to wrap up, actually.
Oh.
If you guys have any questions, I want to encourage you guys to reach out to us. I also want to encourage you to post issues and do polls, ask us to do polls on GitHub. If we forget to post something, let us know, post an issue, we'll get the notification, we'll get it done. Right now, the GitHub repo does not have the data and does not have the slides. We took it out because the network was bad. So those will be going back in. And I also have a VM with a complete setup. I'm trying to figure out how to distribute that because it's 1.9 gigs. So GitHub's really going to...
Put it on S3.
Okay.
When you get on a nice network, because S3 gives you unlimited bandwidth.
Okay. So so please communicate with us via GitHub, and let us help you with your issues.
Yeah, and my Twitter handle is up here. Jackie's handle. Hold on, let me put yours. Jackie Kazil, right?
Yeah. That's awesome.
Yeah. So there's our Twitter handles. Alex does not have a Twitter handle.
Oh, one last thing. I have one jump drive up here, and I think I'm missing one. Okay, and so, okay, great.
Cool. Well, thank you very much. Yeah, if you have any questions, I'm going to be around. I have a book signing tomorrow, so come talk to me then. I got cards up here if you want to take stuff offline. So, thank you very much.